Let's explore a fundamental property of exponents that's crucial in algebra. When k raised to the power of n equals k raised to the power of m, we can conclude that n equals m. This property only holds under specific conditions when k is greater than 0 and k is not equal to 1. These restrictions are important because the property breaks down otherwise. To understand this concept better, let's examine a concrete example using the base 2, which meets our conditions of being positive and not equal to 1. On the left, we know that 2 cubed equals 8. On the right, we have 2 raised to some unknown power x, which also equals 8. By our exponent property, since the bases are the same and the results are equal, the exponents must be equal. Therefore, x must equal 3. Let's visualize this relationship on a graph to see why only x equals 3 can satisfy our equation. This graphical representation will help us understand the uniqueness of the solution. The blue curve represents the exponential function y equals 2 to the power of x. Notice how this function increases rapidly as x increases, which is characteristic of exponential growth. The horizontal red line represents y equals 8, which is the value we're trying to achieve in our equation 2 to the power of x equals 8. The key insight here is that the exponential curve and the horizontal line intersect at exactly one point, where x equals 3. This is because exponential functions with bases greater than 1 are strictly increasing. They never take the same value twice. This graph confirms our algebraic conclusion. The equation 2 to the power of x equals 8 has exactly one solution, which is x equals 3. This is a direct visual demonstration of our exponent property. This uniqueness of solution is not just specific to base 2, but applies to any positive base except 1. When k is positive and not equal to 1, the function k to the power of x is either strictly increasing or strictly decreasing, which means it maps each input to a unique output. For bases between 0 and 1, the exponential function is strictly decreasing, while for bases greater than 1, like in our example with base 2, the function is strictly increasing. Both cases ensure that if k to the power of n equals k to the power of m, then n must equal m. To solidify our understanding, remember that for any positive base k that's not equal to 1, if k raised to the power of n equals k raised to the power of m, then n must equal m. This one-to-one relationship is what makes exponential functions so useful in many mathematical contexts. Let's explore the properties of exponential functions in the form f of x equals k raised to the power of x. These properties will help us understand why k raised to the n equals k raised to the m implies that n equals m when k is positive and not equal to 1. First, let's examine the case where k is greater than 1. When the base of an exponential function is larger than 1, the function exhibits specific behavior that we'll visualize. Here's the graph of f of x equals 2 raised to the x power shown in blue. We've chosen k equals 2 as our example, which is clearly greater than 1. Notice how the curve rises from left to right, indicating growth. To demonstrate that this function is strictly increasing, let's examine specific points on the curve. When x equals 1, we calculate 2 raised to the power of 1, which equals 2. So the function value at this point is 2. Now, when we increase x to 2, we calculate 2 raised to the power of 2, which equals 4. Notice that as our x value increased by 1, our function value doubled from 2 to 4. This pattern continues. For any two x values where one is larger than the other, the function value at the larger x will always be greater. This confirms a fundamental property. Exponential functions with k greater than 1 are strictly increasing. This means that as x increases, the function value always increases as well. Mathematically, if x1 is less than x2, then k raised to the x1 power is less than k raised to the x2 power, whenever k is greater than 1. Now let's examine the case where k is between 0 and 1. When the base is in this range, the exponential function behaves quite differently. Here's the graph of f of x equals 1/2 raised to the x power, shown in red. We've chosen k equals 1/2 as our example, which is clearly between 0 and 1. Notice how this curve falls from left to right, indicating decay rather than growth. To demonstrate that this function is strictly decreasing, let's examine specific points again. When x equals 1, we calculate 1/2 raised to the power of 1, which equals 0.5. So at this point, our function value is 0.5. When we increase x to 2, we calculate 1/2 raised to the power of 2, which equals 0.25. Notice that as our x value increased by 1, our function value was cut in half, going from 0.5 to 0.25. This pattern continues. For any two x values where one is larger than the other, the function value at the larger x will always be smaller. This confirms our second fundamental property. Exponential functions with k between 0 and 1 are strictly decreasing. This means that as x increases, the function value always decreases. Mathematically, if x1 is less than 2, then k raised to the x1 power is greater than k raised to the x2 power, whenever k is between 0 and 1. Now let's examine a crucial property that applies to both cases. These exponential functions are one-to-one. This means that each output value corresponds to exactly one input value, which is key to understanding why k raised to the n equals k raised to the m implies n equals m. To demonstrate this one-to-one property, let's choose a specific y value, say y equals 2, and see how many x values correspond to it on each curve. We'll draw a horizontal line at y equals 2 to see where it intersects our exponential curves. On the blue curve, where k equals 2, we find exactly one intersection point. We can verify that when x equals 1, 2 raised to the power of 1 equals 2. So there's exactly one x value on this curve that gives us y equals 2. Similarly, on the red curve, where k equals 1/2, we find exactly one intersection point. When x equals -1, 1/2 raised to the -1 power equals 2. This is because 1/2 to the -1 equals 1 divided by 1/2, which equals 2. Again, there's exactly one x value that gives us y equals 2. This demonstrates the one-to-one property of exponential functions. Each y value corresponds to exactly one x value. This is true whether k is greater than 1 or between 0 and 1, as long as k is positive and not equal to 1. This property is precisely why if k raised to the n equals k raised to the m, then n must equal m. Since the function is one-to-one, equal outputs can only come from equal inputs. To summarize, exponential functions of the form f of x equals k raised to the x power have three key properties. They're strictly increasing when k is greater than 1, strictly decreasing when k is between 0 and 1, and most importantly, they're one-to-one for all positive values of k, except when k equals 1. These properties together prove that if k raised to the n equals k raised to the m, then n must equal m, as long as k is positive and not equal to 1. Let's examine why k raised to the power of n equals k raised to the power of m implies that n equals m. This property is fundamental in algebra, but it only holds when k is positive and not equal to 1. To prove this relationship, we'll apply the natural logarithm to both sides of the equation. This is a common technique for equations with exponents because logarithms can bring down exponents. So we now have the natural logarithm of k to the power of n equals the natural logarithm of k to the power of m. Using the logarithm property that the log of a power equals the power times the log of the base, we can rewrite our equation. So the natural log of k to the n becomes n times the natural log of k. Similarly, the right side becomes m times the natural log of k. Now, this is where our constraints on k become crucial. Since k is greater than 0 and not equal to 1, we can guarantee that the natural log of k is not equal to 0. For k equals 1, the natural log would be 0, making our next step invalid. And for k less than or equal to 0, the natural log isn't even defined in the real number system. Since the natural log of k is non-zero, we can safely divide both sides of the equation by it. This is essentially applying the same operation to both sides, which maintains the equality. After dividing both sides by the natural log of k, the equation simplifies beautifully to n equals m, which is exactly what we wanted to prove. This elegant proof demonstrates why exponential expressions with the same base must have the same exponent to be equal. It's a powerful result that forms the foundation for solving many types of exponential equations in mathematics. Let's examine a specific example to understand why k raised to the power of n equals k raised to the power of m implies that n equals m. Here we have 3 raised to the power of 4 equals 3 raised to the power of x. We know that 3 raised to the power of 4 equals 81, so we can rewrite our equation as 81 equals 3 raised to the power of x. In this equation, our goal is to solve for x, which will demonstrate the principle that when the same base is raised to different powers and the results are equal, those powers must be equal. One approach is to calculate various powers of 3 to identify which exponent gives us 81. Let's create a table to visualize this. Looking at our table, we can see that when we raise 3 to the power of 4, we get 81. This matches exactly with our equation 81 equals 3 raised to the power of x. Since we found that 3 to the power of 4 equals 81, and our equation states that 3 to the power of x also equals 81, we can conclude that x must equal 4. This demonstrates our key property. When the same base is raised to different powers and yields the same result, those powers must be equal. While this approach works well for simple cases, let's verify our result using logarithms, which provides a more general method for solving exponential equations. When solving exponential equations, taking logarithms of both sides allows us to bring the exponent down as a coefficient, making it easier to isolate. We'll apply logarithm base 10 to both sides of our equation. The choice of base doesn't matter for this proof, but base 10 is commonly used for calculations. Now we can apply a fundamental property of logarithms. The logarithm of a number raised to a power equals the power times the logarithm of the number. So log base 10 of 3 raised to the power of x equals x times log base 10 of 3. Let's calculate these logarithm values. Using a calculator, we find that log base 10 of 81 is approximately 1.908, and log base 10 of 3 is approximately 0.477. Now we can solve for x by dividing log base 10 of 81 by log base 10 of 3. This gives us 1.908 divided by 0.477, which equals 4. Using the logarithmic method, we've confirmed that x equals 4. This mathematical approach works for any exponential equation where the bases are the same. The logarithmic method provides a rigorous proof of our answer. By converting the exponential equation to a linear one through logarithms, we can precisely determine the value of the exponent. This example illustrates the general property that when k raised to the power of n equals k raised to the power of m, then n must equal m, provided that k is positive and not equal to 1. This restriction on k ensures that the exponential function is 1 to 1, meaning each output corresponds to exactly one input. The logarithmic approach we've used here is powerful because it works for any exponential equation with the same base, regardless of whether the exponents result in nice whole numbers. Let's examine some important counterexamples to understand when the property k to the power of n equals k to the power of m implies n equals m holds true. These counterexamples will reveal why we need specific constraints on k. Our first counterexample involves the case where k equals 1. This is a special value that behaves differently from other numbers in exponentiation. When k equals 1, we have the equation 1 raised to the power n equals 1 raised to the power m. Let's think about why this is interesting. Looking at some examples, we can see that 1 raised to the power of 2 equals 1 raised to the power of 3 equals 1 raised to the power of 100, and they all equal 1. This happens because any number raised to any power always gives back that same number. Let's visualize this concept on a number line. No matter which exponent we choose, whether it's 1, 2, 3, or 4, the value of 1 raised to that power always equals 1, placing all results at exactly the same point on our number line. This demonstrates an important insight. When k equals 1, n does not have to equal m for the equation to be true. For instance, 1 raised to the power of 5 equals 1 raised to the power of 100, but clearly 5 does not equal 100. This is why k cannot equal 1 for our original property to hold. Having examined our first counterexample, let's move on to another important case that challenges our original property. Our second counterexample explores what happens when k equals 0. 0 has unique behavior when used as a base in exponentiation. When k equals 0, we're looking at the equation 0 raised to the power n equals 0 raised to the power m. Let's investigate what this means. For positive exponents, we can see that 0 raised to the power of 1 equals 0 raised to the power of 2 equals 0 raised to the power of 10, and they all equal 0. This makes sense because multiplying 0 by itself any number of times will always give 0. We should note an important exception. 0 raised to the power of 0 is a special case in mathematics. It's either considered undefined or in some contexts defined as 1 by convention. This is why we specifically focus on positive exponents for this counterexample. Similar to our first case, this demonstrates that when k equals 0 and we're dealing with positive values for n and m, they don't need to be equal for the equation to be true. For example, 0 raised to the power of 2 equals 0 raised to the power of 5, but 2 doesn't equal 5. Having examined these two critical counterexamples, we can now synthesize what we've learned to understand the constraints on our original property. Our exploration reveals that the statement, if k to the power of n equals k to the power of m, then n must equal m, is only true when k is greater than 0 and k is not equal to 1. These are necessary conditions for the property to hold. These constraints are mathematically necessary because we've just demonstrated that when k equals 1 or when k equals 0, we can have different exponents that yield the same result. The uniqueness property of exponents only works when k is positive and not equal to 1. Let's summarize our findings. We've examined two key counterexamples, the cases where k equals 1 and where k equals 0. These cases show us why the constraints on k are essential for the property to hold true. In conclusion, the property that k to the power of n equals k to the power of m implies n equals m is only valid under specific conditions. These conditions, that k must be positive and not equal to 1, are essential for the uniqueness property of exponents that we often take for granted in algebra. Let's explore an important property of exponential functions that enables us to solve many types of equations, the fact that they are one-to-one functions. To visualize this property, we'll examine two different exponential functions on a coordinate plane. Here's our first function f of x equals 2 to the x power in blue. Notice how it starts near 0 for negative values of x and grows rapidly as x increases. This is characteristic of exponential growth. And here's our second function g of x equals 0.5 to the x power in green. This function displays exponential decay, decreasing as x increases. Interestingly, it's a reflection of the blue curve across the y-axis. Now, let's apply what's called the horizontal line test to determine if these functions are one-to-one. I'll draw a horizontal line at y equals 4. A function is one-to-one if every horizontal line intersects the graph at most once. Looking at our horizontal line, we can see it intersects the blue curve exactly once at the point where x equals 2. This means 2 to the power of 2 equals 4. For the green curve, we have just one intersection at x equals negative 2, where 0.5 to the power of negative 2 equals 4. This illustrates the crucial one-to-one property of exponential functions. Each output value corresponds to exactly one input value. No matter which horizontal line we draw, it will always intersect our exponential curve exactly once. This property holds true for any exponential function k to the x power, as long as k is positive and not equal to 1. From this one-to-one property comes our key theorem. If k to the power of n equals k to the power of m, then n must equal m. This only works when k is positive and not equal to 1. Think about it. If the same base raised to different powers gives the same result, those powers must be equal, precisely because exponential functions are one-to-one. This property is what allows us to solve exponential equations by taking logarithms of both sides. When we have an equation like 3 to the x power equals 27, we can take the logarithm of both sides to isolate x. And we're guaranteed a unique solution because of this one-to-one property. Understanding that exponential functions are one-to-one is fundamental to working with exponential equations. It's what guarantees that when k to the n power equals k to the m power, n must equal m, giving us a powerful tool for simplifying and solving exponential relationships.